All right, good morning. So once in a while, just to satisfy my curiosity, I check what is happening on a WebAssign. For many years I've done that. And when I feel something odd, I check it. And if I check it for one student, I'm required to check it for all students. And if I check it for one class, one lecture, I'm required to check it for all lectures. And WebAssign collects a lot of specific information. For example, here, a student spent 1 minute on a WebAssign answering one question. I can't assign a full participation for that, can I? I don't think so. Another example, a student logged in from Comcast. That's not a BU network. And in 1 minute answered 6 questions in a row. What does it mean? I don't know, but it doesn't look to me like participating. So once in a while, I check WebAssign data, all of it. There is a simple algorithm which I use to find anything odd. And that algorithm set odd things to 0. So, of course, mistakes may happen. Mistakes may happen. And if you are absolutely sure you've been present, but your participation grade is lower than you think it should be, just send me an email. I cross-reference, I'll check everything I can. Most probably you will be right. Maybe not. Things happen. So, another example when feelings actually helpful. Yesterday, right after the lecture, when I left, I had a feeling something went wrong. And it wasn't related to technical issues. Technical issues, not issues. It happens. It was related to something conceptual. So I gave my brain a task, figure it out. 30 minutes later, when I was actually driving to a meeting, this slide came right in front of my eyes. I made a mistake, and I knew it. And well, of course, if we made a mistake, we have to fix it. You know what? Yes. So the mistake is actually really kind of simple. A cosine is a symmetrical function. There is another point with exactly the same value, but that point is located on another side of the vertical axis. So it looks like it is located in a negative time. Here, exactly the same value. But the thing is that we're actually shifting this point, and that's how it's supposed to be shifted, to the right. And there is, of course, the easy check. I just had to choose another instant, for example, t equals 1, and calculate x at t equals 1, 7 times cosine pi over 4 minus pi over 4, 0, which gives 7, which means at t equals 1, now we should observe the maximum. So the fix is, of course, very easy to make, but the minus says shift it to the right. So after having felt twice, I Googled this, when feelings may play an important role. And one of the top answers is, when it comes to learning, I didn't read this, so I don't know what it means, but you can just repeat this, search, and read it. Turns out many, many answers tell us that emotions may play an important role. I wouldn't know. Okay, so Question to you, please. That's what we talked about last lesson at the very end. The potential energy of an object making simple harmonic motion changes in time and with location, and the kinetic energy, but total energy, neglecting friction, remains the same. And now, what would you say? How many joules in this situation does potential energy have if this cart, the mass of this cart is 250 grams, travels at 4 meters per second through the equilibrium? That's what we know. How did we measure it? Force sensor or no? You will be using force sensor and the ultrasonic motion sensor in a lab. But to measure speed, we need only motion sensor. The motion sensor gives us instantaneous location, instantaneous speed, even instantaneous acceleration. So we've measured it, and turns out when the cart was traveling through the equilibrium, the speed was 4 meters per second. So now, if you use this information, please calculate the maximum potential energy of this cart. And enter your answer. In joules. And a joule is a unit of international system of units. It's a Newton times the meter. And a Newton also is a combination of a kilogram, meter, and second, well, over second squared. So this is an actual problem you have to solve. And to do that, you have to use not your brain, your hand. If you're a right-handed person, you should use your right hand. If you're a left-handed person, you should use your left hand. Write an equation, plug in numbers, calculate, discuss it with your friend or enemy. Pick a number, enter the number. Also, I found some students used to answer for all questions, answer number one, no matter what. Well, my theory is student testing probability theory, figuring out how many times it would be right. So here, if we want to calculate potential energy directly, we would have to use this expression. In particular, the maximum value is reached when the object reaches the amplitude away from the equilibrium. However, we have no information neither about the spring constant nor the amplitude, which forces us to look for a different approach. And we start looking for connections. That's what we always do. when we need to solve a problem. Potential energy is related to a spring constant, to the x-coordinate of a card. There is, of course, a natural assumption. What natural assumption? Well, we have several natural assumptions. For example, the motion is happening and observed relative to the ground. Normally, it's not written. We just assume it. Second, anything is happening on this planet. So G equals 9.8 or about 10. There is no air friction. And in this situation, the natural assumption is that the origin is chosen at the equilibrium location. What would be different if that wouldn't be a case? Well, we couldn't use a letter x. We would have to use the symbol delta x, which says the x-coordinate is measured from the actual equilibrium coordinate. So, okay, this path didn't work, so we have to start looking for additional connections. Well, it's energy, so there's another set of connections. Potential energy is related to mechanical energy. It is related to kinetic energy. So we may need to explore these connections. And mechanical energy, as we know, by definition, is equal to the sum of kinetic and potential energies. And, all right, what else do we know? Mechanical energy might remain constant or change. It depends on what? Friction. In general, we should say non-conservative forces. Who knows what it means? We know what friction means. So, no friction, mechanical energy conserved. That's another natural assumption for every problem like that. And that means we can apply the law of conservation of energy to two most important locations, the equilibrium and the extreme location when the object is away, the amplitude away from the equilibrium. At the equilibrium, mechanical energy should be equal to maximum potential, maximum kinetic, sorry. Someone sneezed and that scared me. Maximum kinetic. I'm easily scared, as you can see. And at the extreme location, it stops. When it stops, there is no kinetic. So all energy becomes equal to maximum potential. But it has to be exactly the same value. It has to. So we don't really have to calculate P max. We just have to calculate maximum kinetic energy, and that will be equal to maximum potential energy, and that will be equal to total mechanical energy of this system, because there is no friction. And now we know this strategy, because kinetic energy is also related to other variables, mass and speed. Kinetic energy maximum will be equal to mv maximum squared over 2, which is, well, don't forget, we have to use kilograms, 0.25 times 4 squared over 2. So 0.25 is 1/4, 4 squared over 4 over 2, 2 joules. Of course, the problem is simple, but the strategy, as you can see, well, involves many important steps. So if you absorb the strategy, you can solve practically any problem involving energy conservation, including this one. We used this relationship already at least twice. I promised I would prove it. A promise is a promise. I have to prove it. But we basically just did it. We just didn't make a couple of more steps. So that's equilibrium, x equals 0. That's the maximum displacement from equilibrium, x equals a. And as we said, kinetic energy at the equilibrium should be equal to potential energy at the farthest location from equilibrium. So algebraically, that means that maximum kinetic energy, mv max squared over 2, should be equal to maximum kinetic energy, Ka squared over 2. And now we just solve it for the maximum speed. 2 and 2 getting cancelled. So and the square root of ratio of spring constant over mass, that's by definition is angular frequency. So now we have proved all relationships we've used before. Well, so now let's just solve a very specific problem, but it's a very typical problem. We can calculate now lots of things, so we just have to do it step by step. First, as you remember, we've considered two special cases. One special case is related to a situation when object was pushed when it was initially sitting at the equilibrium. And second situation, when the object was released from rest away from equilibrium. So we call them case 1, case 2. Case 1, released from rest. Case 2, pushed. This equation tells us what is happening. What case is being described here? Case number 1 or case number 2? What do you think? This type of reasoning brings an important relationship between mathematical equation, which is completely abstract entity, and the actual real world motion of an actual object. So it's important link. So what do you think? Case 1 or case 2? 1. We just check what is happening at t equals 0. Cosine of 0 is 1. So at t equals 0, at the initial instant, the cart or object was located at x equals 5, and that is the maximum value for x. Why? Because maximum value for cosine is 1. It cannot be any larger. So this is a case 1 situation, yeah? Which means the initial speed should be 0. We actually can write the equations. But first, let's extract all information. So for example, amplitude. And we assume that everything is measured in meters, seconds, radians, kilograms. So amplitude, what number should I write for the amplitude? What does the gentleman in the white shirt think? What number should I write for the amplitude? Okay, you moved. Now you moved again. What number should I write for the amplitude? I can just hear you. Say it loud.
10.
Wrong. Sorry. The lady was correct. So you should look at the graph. That's a good exercise to sketch a graph. And the graph for cosine begins, well, for this cosine begins at 5, goes to 0, goes to -5, and goes back to 0 and to 5 again. And your answer assumes that people call amplitude this span. No, the official definition of the amplitude is maximum displacement from equilibrium, which means in this situation from 0. That's what we call amplitude. So according to the definition, that should be equal to 5 meters. But the distance traveled from one extreme location to another extreme location, distance between two amplitudes, that will be equal to 10 meters. So, for example, I can ask you, please tell me distance traveled by this cart in one period. What number should you say? How many meters does it travel in exactly one period? What do you think? 20 meters? One period is an equivalent of 4 quarters, and for each quarter of a period, this car travels exactly 5 meters. We started, well, let's say it's 5 meters, so 5, 5, 5, 5, or 20, 10 and 10, 20. There is a standard question in a problem like that. Calculate the distance traveled in a minute, for example. Distance traveled in 1 minute. We will calculate it. How? Well, we know that in one period, it travels 20 meters. So if we knew how many periods are in 1 minute, we could just multiply the number of periods, the number of oscillations, times 20 meters. How do we calculate the number of oscillations? Well, we have to relate it to the period. The period, by definition, is equal to time of a certain number of oscillations divided by that number. So this is how we should calculate the number of oscillations times the distance traveled per period, which is 20. And time is 1 minute or 60 seconds. So if we knew a period, that would solve this particular problem. This is a very typical situation. Do we know a period? No. Nowhere. So we need it, but we don't know it. What do we have to do? What do we have to do? Like money. You need it, but you don't have it. What do? You find it. So we need this variable to make a next step, but we don't know it. So that means we are refocusing our attention from what we were looking for initially to what is now our new immediate goal. So we start thinking about period again, but now we have to relate it to something else, and we start remembering connections. The period is also related to frequency or angular frequency. Well, frequency and period are inversely proportional, and angular frequency and the period are inversely proportional with the coefficient of 2 pi. Personally, I prefer a mnemonic rule to use every time. This product is always equal to the same constant. Angular frequency times period equals 2 pi radians. And I can use it backwards and forward to calculate period from angular frequency. So if I need to calculate the period from angular frequency, I need to know angular frequency. We again came up to same situation. We need it, but we don't know it. So we have to find it. And find now means different. We don't use a specific equation. We use a different relationship. We'll look at the equation. And the equation tells us what angular frequency is for this particular object. So angular frequency is equal to what? pi over 2. And to see that, the best way is to rewrite the equation to separate time variable from everything else. So now this coefficient, which we see right in front of time, that's the angular frequency. And that is radians per second automatically. So now we can finish our calculation of the period. 2 pi over 2. So many pi's. I'm getting hungry. Pi and pi cancels. 2 times 2, 4 seconds. Now we can use this number to finish our initial question. What is the distance traveled in 1 minute? So 60 seconds over 4 times 20 meters. So 15 times 20, 300 meters. Amplitude, angular frequency, period, well, regular frequency will be equal to 1 divided by the period, so 1 over 4, or 0.25 hertz. Now, it's very, again, easy to calculate maximum values. Vmax, I'm not going to do it. I'm just going to write again, equals amplitude times angular frequency, multiply two numbers. Maximum acceleration equals amplitude times omega squared, multiply two numbers. Next part, maximum force. Well, the maximum force is reached when the object is at maximum displacement, A times A. We know amplitude, but we don't know K. So we need it. We don't have it. We have to find it. And there is always a question which I always ask myself, even not out loud. What can I do now to find what I need to find? What can I do now? Well, I have to start searching for relationships between this variable and other. And we know it is related to mass. It is related to angular frequency. By definition of angular frequency, so to calculate spring constant, we just have to multiply two numbers again. And we know the mass, and we know angular frequency, so done. We just did this a couple of slides ago. K times A squared over 2, mv squared over 2. Same. They actually all will be equal to each other. It doesn't matter how we calculate them. So the most interesting part starts here. All right, I'm going to need a new slide with that. Well, calculating quantities at a given instant requires just using your calculator correctly. That's it. For example, x at t equals 1 is equal to 5 times cosine pi times 1 over 2. Please take a calculator and calculate it as an exercise. You should expect that at least one during the lecture you will use your calculator, so you can just take it out of your backpack immediately after arriving and having a seat. You're going to do it anyway. So please, several students, please, anybody, tell me your answers. What's your answer? Okay, your answer is 0. What is your answer? Do we have an answer? No answer. That's also an answer. What is your answer? Yes. No, I asked that gentleman in the glasses. You can say, I don't know, 0. It's either or. Well, but I don't know is basically no answer. So if anybody has a different answer, please just tell me a number. Yes? 4.998. Thank you. And same? Okay. Well, 3 is already good for voting. So now just please raise your hand if your answer is 0. Thank you. If your answer is wherever, error, no answer, not sure what to do, please raise your hand. If your answer is 4.998, thank you. So you will get only partial credit because you didn't switch your calculator from degrees to radians. Because pi is 3.14, 15, 96, etc., etc. Assumes radians. So technically, this is wrong. So you have always 2 options. Just keep an eye on units. The option number 1, switch your calculator to radians. The option number 2, convert radians to degrees. For example, pi over 2 radians in degrees, what number is that? 90. So in that case, if you calculate x equals 5 times cosine 90 degrees, 0. So just keep an eye on units. All right, moving on. Well, now what we can do is plug in any time in the calculator and just calculate. Now you know you have to pay attention to the mode. That's it. So 5 times cosine pi over 2 times sine for any time. What about velocity? Well, we know because we remember the graphs. Graphs help. This is the graph for position. But we remember that velocity starts from 0 for this situation, and it goes in the negative area first because it points to the left initially. So it should be a sign, and the acceleration is x, is flipped x, basically. It looks like this. So velocity equals maximum velocity times sine times the minus, because it should go in the negative region, and same angular frequency. That's the equation for velocity. Acceleration, strictly speaking, the x component of velocity and x component of acceleration. It equals negative omega squared times x, as we know. So it's negative a omega squared cosine pi over 2 times time. And these equations will tell you any value for any time, any t. So now it's very straightforward calculation. Just keep an eye on radians, degrees, and degrees. All right. And now we need to figure out something about time when something had happened. For example, well, something happened at x equals 1.25. Of course, it happens at a certain instant. So we can use the motion equation, for example, backwards for calculating when did it happen. And then we can use that time for calculating speed and acceleration. So let's say x equals 1.25. X equals 1.25. So the motion equation says it should happen when five times cosine of pi over 2 times this specific instant equals 1.25. So what do? Well, we have to solve it. So 1.25 over 5 should be equal to cosine of that particular expression. I believe that's 1/4. 1.25 over 5, 1 over 4, or 0.25. Please tell me if my belief is right or wrong. Okay. Now what do? Well, our calculator has the inverse function. So the inverse cosine of 0.25 should be equal to pi over 2 times this particular instant we're looking for. And what does the calculator say? So you press, well, I press second function, cosine, parentheses, 0.25 equals, and my answer is, what is your answer? Exactly like mine. And now 75.52 times 2 over pi is equal to that very time we are looking for. You think, or you sure? So why do you say I think? You're absolutely right. Yeah. If you look closely, the calculator tells DEG means degrees, but pi is in radians. So this a fraction has mixed units, which is wrong. Technically, we could correct it easily. We just have to remember those degrees and those are radians. So we still can make it work. We just have to convert radians into degrees or degrees into radians. Doesn't really matter. So for me, if I use this approach, it's easier to convert radians into degrees because pi radians is 180 degrees. Or another approach would be switching your calculator to radians first, and in that case, instead of 75.52, you would have a different number in radians automatically. So now we can finish this calculation. I want to do it as accurate as possible. So I want to start from scratch. Second function, cosine, open parenthesis, 0.25, close parenthesis, times 2, divided by second function, 3, it gives me pi equals I didn't press parentheses. .84, right? Something like that. Let's check it. I'm not sure. I don't remember the answer. I have solved it a year ago. So, seconds. Okay. No, too soon. So I want to insert an extra slide. All right, so okay, the equation is x equals 5 times cosine pi over 2 times time. And this is the graph. That's one period, which is equal to 4 seconds. So a half of a period will be 2 seconds, and a quarter of a period will be exactly 1 second, 1 second. So 1, 2, 3 seconds, 4. Now, the amplitude is equal to 5 meters. And 1/4 of the amplitude, 1.25, is a quarter of the amplitude. It's somewhere here. This is 1.25. So starting from initial location, 5 meters away from the equilibrium, the object starts traveling toward the equilibrium, and this is how much time it takes to reach this location at x equals 1.25 of a meter. This is the first instant it happens. And it makes sense now. Our number was about 0.8, which is slightly less than 1 second. You look at the graph, you can see it. However, it's not the only time when it happens. The next time it happens here. And if it keeps moving back and forth, it's going to reach the same location again and again and again, and you can see when it's going to happen again and again and again. So, for example, if I ask you, when is going to be the next time? Well, the next time will be here, 3 seconds plus 0.8, so at 3.8 seconds. The calculator gives you only one possible answer, the smallest one. But if you look at the graph, you can figure out all other possible times when the same location is reached. Plus, if you look at the graph, you know that first time the car travels through this location to the left. Velocity points to the left. How do we know it? Well, for example, we can look at the slope. The slope is negative. And the second time, the same car travels to the right. And so we have it released from rest to the right, 5 meters. We released it. And first time it's here, traveling to the left. And it goes all the way to the negative amplitude, goes back. And second time it's here, traveling to the right. Yes? At t equals 3 seconds, the car is at equilibrium. And then, right from equilibrium, it reaches 1.25. Not sure I understand your meaning. Maybe you're right, maybe you're wrong. I'm just not sure. Please, can you tell me?
The question is, the first time that it reaches at 1.25 displacement, that's 0.8. So what's the next time? Time is after 3 seconds. But this time should be closer to 3 seconds than it should be to 4 seconds.
we should add a half of a period. We should add 0.8, 1, 2, 3, 1.25 over 5 should be equal to inverse cosine of it, should be equal to pi over 2 times this time, plus or minus 2 pi. Plus or minus 2 pi radians. So that's supposed to be the total solution. So that was, so we need to multiply by 2, divide by pi, times inverse cosine of 0.25, minus or plus, this is the cosine, this is the first time, so cosine, this is the first time is reached, this is the second time is reached. So this is what we should add. This is the same cosine, 1, 2. So this is the equivalent of 0.8. This is the equivalent of 0.8, and the total period is 4, which is 1 whole revolution.
4 minus 0.8. Plus 0.8 is equivalent to taking the negative y-axis.
So it only means, yeah, my graph is probably very, very skewed because I don't see it from my graph. Mathematically, well, first of all, we can always check it by direct calculation. Oh, now I see it. Again, this is 0.8, this is 0.8. And in my mind, I looked at this and I thought this was 0.8. Because if I made a mistake, I need to figure out what went wrong. This is what went wrong. My mind played trick on me. This is not 0.8. This is 0.8. And I have to subtract the same amount from 4. Absolutely right. So 3 seconds, and that will be 4 minus 0.8, 3.2 seconds. Thank you, and thank you. And this is a good illustration how little things in your graph may confuse you, if they confused me, you know, who've been doing it for a long, long time. But as I've told you, my brain doesn't work in the morning, so as efficiently as it should be. All right, perfect. Now we are all on the same page. Now I can add an additional page because this page has been used up. What else did I want to do? So same equation, 5 times cosine pi over 2 times time. Same graph. There are several special locations, like 1/4 of the amplitude. But of course, there is another interesting location, 1/2 of the amplitude, which is 2.5 in this example. So the graph actually tells you immediately at least what range should be that for that time when it happens. We know that 1/4 of a period here is equal to 1 second. Now, if this cart would be traveling like this, a straight line represents motion with a constant velocity. If it travels with constant velocity, it travels same distance in same time. So it would reach 1/2 of the amplitude at 1/2 of the time. That would have been 1/8 of the period. But in reality, the actual graph is different. So the actual time when the 1/2 of the amplitude is reached is supposed to be somewhere here between 1/8 and 1/4. Well, of course, what is the actual value for this? Well, we just have to solve an equation. 1/2 of the amplitude is equal to the amplitude. It actually doesn't matter what amplitude is equal to because it's getting canceled. Times cosine of pi over 2 times this time with 2 stars. So 1/2 equals cosine pi over 2 times this instant. So we have to calculate the inverse cosine of 1/2. And the inverse cosine of 1/2. Now, you know, you have to get degrees and convert it into radians, or you have to switch your calculator into radians. My calculator tells it should be 60 degrees or pi over 3 radians. Right? So seconds. There is an algebraical way to do it in general. So I just want to show it once. A over 2 will be equal to, this is an example when we know x. In this particular example, x is equals to 1/2 of the amplitude. A over 2 equals 8 times. And the equation which we use in general looks like this, cosine of omega times time. But if we cancel the amplitude, and if we use the relationship between the angular frequency and the period, angular frequency equals 2 pi over a period. And we are looking for this specific instant. So if we solve it algebraically, pi over 3 should be equal to 2 pi over a period times that specific instant. And now pi and pi cancels, so that specific instant is reached at 1/6 of the period. So this is an illustration that sometimes, again, we don't really need to know some variables like amplitude to answer a question about location or a time. Doesn't matter. Location equals 1/4 of amplitude. Time equals something else. Location equals 1/2 of the amplitude. Time equals 1/6 of the period. For the quarter, we can solve it in exactly the same way. What is happening to speed or acceleration? Well, for that, you can employ exactly the same reasoning. And you can use an equation and just literally solve the equation. Or you can sketch a graph and look at the graph like this one. All right. I don't want to. Come on. So just, again, a simple last illustration for velocity. Velocity starts from 0 and goes to some maximum value, goes back to 0 and again, and again, and again 1/4 of a period, is equal to 1 second. So this is when the maximum speed is reached the first time. Yeah. So when 1/2 of that is reached, well, the graph tells us, that again, it should be somewhere between 1/2 and now a 0. This is when it's reached the first time. For the motion, it's constant velocity. Constant velocity, it would be reached at 1/2 of a period, but for simple harmonic motion, it is reached before that. So the graph tells us immediately, but of course we always can write an equation. Plug in any value we want to, for example, 1/2 of the maximum, and solve it. I would recommend at home try both approaches, geometrical, graphical, and algebraical as well, to see that you're confident and you get the same results and you don't make mistakes like I made before, confusing parts of the graphs. All right, oscillations. So we know that any system with a stable equilibrium can be described technically by exactly the same equations. In particular, if you have a cart attached by 2 springs, still we can imagine that there's a single spring making it move. And the relationship, of course, is simple. The actual system and our effective system should have the same mass, the same period. And then we can apply all the theory we have learned to that effective system. Another interesting case is a vertical harmonic motion. So if we have a spring and we have a weight attached to it, the spring is coming right now. First of all, we need to remember the empty spring has no interest for us. We have to attach a weight to it because this is our system. And here, we can and should choose the equilibrium and origin, 0. And now, if we deflect it, pull down or up and let it go, it starts oscillating up and down, up and down, up and down. Now, the oscillation, the period, of course, depends on the mass. This is the new equilibrium now. If I change the mass, I should shift my equilibrium to the new, my origin to the new equilibrium. And I can see that now, with the more mass, the period is larger, frequency is smaller. Well, if we set equilibrium here, what forces do we have acting on this weight in equilibrium when it's at rest? Gravity and elastic. And they should have exactly the same magnitudes. Rest. And this force acting from the spring on this weight should be equal to the spring constant times the magnitude of the displacement. In this particular example, it's 10 centimeters. And what can we do now? Well, now we can imagine that we deflected this weight from equilibrium and let it move up and down, up and down. And very straightforward algebra tells us that the equation which describes this motion has exactly the same structure as the equation for the horizontal motion. The only difference is a letter. Instead of using X, we're using Y. But mathematics cannot depend on what letter we use. We can use any letter. We can use Greek letters, Russian, Portuguese. Doesn't matter. So if the equation is the same, that means the solution is the same. So nothing new we need to learn about vertical spring, nothing new. For example, in this situation, what do? We pull the spring down by 5 centimeters. So the origin is set at the equilibrium, and the initial location is here, and it equals to negative 5 centimeters, or negative 0.05 in meters. Why it's supposed to be negative? Because it's below 0. That's it. So now we can write the motion equation immediately. Y will be equal to we have to write a negative sign. We have to write the amplitude, which is 5 centimeters or 0.05 over meter, times we have to choose the function cosine or sine. In this situation, we have to choose cosine because we release it from rest. And the only variable which needs to be found is this angular frequency, which is supposed to be equal to square root of spring constant over mass. And, well, the mass is given 40 grams or 0.04 over kilograms. And how do we calculate the spring constant? Well, again, initially, when the weight was resting, force of gravity and elastic force had exactly the same magnitudes. So we can solve this for the constant. Mass is 0.04, g equals about 10, and the elongation of the spring was 10 centimeters or 0.1. So done, done, done. And if we know the motion equation, we can answer all possible questions because we know now how to do that. Everything is in the equation. Another system, a pendulum. A pendulum is something which swings on a string, or not necessarily on a string, maybe on a pivot, about the pivot. And we don't have to learn anything new about it, because a pendulum just an object which makes rotational motion, or even simpler, just circular motion. So what do we know about rotational motion? Everything. So let's say this object is kind of nailed, yeah, at a certain location, deflected, and let move. We know that there is a force of gravity acting on it, applied to the center of gravity or center of mass. And we know that this force exerts a torque about this particular axis. We learned it a couple of weeks ago. So the equation which describes the motion of this system is basically net torque equals rotational inertia times angular acceleration. Well, we can repeat all the work. This is the lever arm. The tricky part is that in general, it doesn't have to be a disk or a sphere or whatever it is. So this variable might have a very complicated structure, but we don't care, because instead of, well, this is just a principle. Instead of talking about the actual so-called physical pendulum when an actual physical object is moving back and forth, we can just talk about simpler situation, simple pendulum, a massless string with a massive but very small object attached. And in this situation, we can repeat the same reasoning we used before when we talked about torque, angular acceleration, angular displacement. So my picture demonstrates counterclockwise angular displacement. So the displacement instantaneously at this instant positive. However, my picture also demonstrates that the torque and hence angular acceleration are clockwise, which means again angular acceleration will be related to angular displacement with a minus in between. The equation we used to use for simple harmonic motion of a cart looked like this. But this, the equation which describes the motion of a simple pendulum looks like this. However, only for small angles. Now, you don't have to do all this calculation. It can be done. The result is this. For a simple pendulum, like any of these three balls attached to a string, the angular frequency is directly related to the length of the string and the value of the gravitational acceleration. So in the outer space, the pendulum wouldn't move. We deflect it, it remains in that position. On the moon, it would swing differently because on the moon, g equals 1/6 of the g on the Earth. So it depends on the planet, and it depends on the length. And now you can answer this question. Finally, one more question. You look at two pendula The first one is heavy, second is lighter, but they attach to the spring, which makes the center of mass of each ball on the same level. How does it affect the period? Well, the answer is, what do you think? What do you think? Doesn't. Neither of these equations include mass. There is no dependence on mass. So if the center of mass of each ball is exactly on the same level, they should have exactly the same period. Next question. So, same. Now, and take this off. A different situation. Two balls are attached to the same two balls with the same mass are attached to different strings. One is longer, one is shorter. How does it affect the period? The answer is in the equation. When you increasing the length, you're decreasing frequency. So it's have to move slower. And, well, of course, it's very easy to check by direct experiment. In this situation, actually, because the string is 4 times longer, the period will be twice of this. 1, 2, 1, 2, 1, 2, 1, 2. Well, and to finish our talk about oscillations, which is exactly what I planned, let's talk about one specific example. We call it driven oscillations. So this is a case, what we call a simple harmonic motion, when only the restoring force is acting on this object, nothing else. But what can we do? We actually can attach an additional element connected to a motor, for example, or just hit this object every time. So we might drive the oscillations. Turns out applying an additional force doesn't always help. Sometimes it does, sometimes it doesn't. It actually depends on the frequency of the applied force. This object has its own natural frequency. Yeah? Like a vertical spring, if we know the mass, if we know spring constant, we can calculate that natural frequency. This is the natural frequency. And if I drive it with a lower or higher frequency, what's going to happen? How does it affect it? Well, it is smiling. Finally, something is happening. It was sitting on a shelf. So I'm driving it at actually 10 hertz. Spending some energy, applying some force, but nothing really happening. I saw that the natural frequency was about, well, maybe 1 or 2 oscillations per second. So what I want to do, I want to decrease the driving frequency, make it closer and closer to the natural frequency. 7 now. Two. 1.8. Well, I can see something starts happening. 1.5. we can see that the amplitude increases and it actually doesn't oscillate anymore. The system broke, basically. So this is what we call resonance. When the frequency of the external driving force reaches the natural frequency of the system, the energy getting pumped in the system in phase with the energy which has been stored already in the system, which makes the system move with larger and larger amplitudes. We call it a resonance. And the resonance actually might lead to very destructive events. If you look at this video, you can see how the bridge starts moving and eventually breaks. And that is one of the reasons why, for example, when troops walk on the bridge, they don't march, because there is always a chance if they march, they might hit the natural frequency of the bridge, and everything oscillates. Even if the initial amplitude is very small, if the natural frequency is hit, more and more energy might be transferred to the system, and eventually the system might break. But the resonance also is a good thing because it can be used to amplify signals, what is happening in different radio circuits. Done with oscillations. Any questions? So we start in a new topic related to fluids, first static fluids, and specifically objects in fluids. And I got a question which is not related to anything new. It is related to your knowledge of forces and experience of drawing free body diagrams. You have a bucket with water and you immerse a ball which is attached to a string or a spring, and what would be the free body diagram for that object when that object is in water or any other fluid? So, of course, first you have to draw your own diagram, then you have to look at it, and then you have to compare your diagram with any of the given diagrams, and if you see your diagram, you choose whatever number you see. If your diagram is different from any of these, you choose 6, none of the above. That's how it should be done. And now, you also have to take a photograph of your diagram and email it to me. Again, this is my BU email address, VALBU and BU.edu. I wasn't sure if I would have time today to start this topic, but just in case, I've prepared some toys. Today I'm going to use only scale and a ball, which you see on the screen, a bucket. Of course, I need to fill up this bucket with water. And you can see the scale shows the mass of this water with the bucket. You see? It's a very expensive experiment. Just to make it more visible. Okay. So right now, when I attach the ball to the spring scale, like in the original situation, we can see the weight of this ball is equal to about 11 newtons. And how many forces right now are acting on it? 2. Gravity and string tension. And ideally, we shouldn't think about the answer to this question. That should be already imprinted in our brain. Free body diagrams, it's lesson 4 and after. So 2 forces. Now, you can look at this scale or at that scale. What's going to happen? Changes. This value goes up, this value goes down, and actually if you compare the values, they change by exactly the same amount, which is important. We'll talk about it tomorrow. But more importantly, to answer this question, this value changed. That means, in addition to 2 original forces, there has to be something else acting on it. So when the ball is in the liquid, how many forces should act on it? 3. Do you see any picture with 3 arrows? No. So the answer is none of the above. The answer is none of the above. And of course, we have to draw the right diagram. So the initial situation shows only 2 forces acting on this ball. And we know that in equilibrium, force of tension, which we read, the reading here on the scale, whatever number is it, it was actually 11 newtons in this experiment. Yeah. Is equal to mg. But now what we do, we have the same ball in water. So now, how does it change force of gravity? It doesn't. Force of gravity depends on mass, and G, still 11 newtons. But we could read that the force of tension changed. It wasn't 11 anymore. It was actually about 2 newtons. That could only happen because a third force, not Republicans, not Democrats, started acting on it. The third force, every force has its source. And what is the source for the third force? U in politics. Water in the bucket. Not the buoyancy. The buoyancy is the name of the phenomenon. But the actual source is always an object. We can touch it. If you touch it, you feel wet. It's water. Water is acting on this ball, exerting that force, which has a name, the buoyant force. However, actually right now we can say immediately that in this experiment, the magnitude of two forces which point up should still be equal to the magnitude of one force pointing down. So this simple experiment immediately tells us how to calculate the buoyant force acting on this object if we read all the values. Now, we had a scale under the bucket, and that reading also has changed. It was 11 newtons. How did it change? Well, now, of course, we have an additional force acting on the scale, and that additional force has the same magnitude as the buoyant force because of the Newton's third law. And now we only have to study the properties of this new force, what it depends on, how else can we calculate it, what if we don't know some of these readings. That's what we're going to talk about tomorrow. All right. Thank you. We're done. Yes. Excuse me. Either way.
Either way? Okay, thank you.
Yes.
I didn't pick up my exam yesterday.
What did you do?
I wasn't here yesterday, so I didn't grab my exam.
No quick questions. Yeah, I'm going to leave right now. And I'm going to go to, right now after I leave, I'm going to go to do my office hours. And we can talk there.
Okay.
Yes.
Professor, the due time for this lecture web assign was 9:53. So I tried to enter question 5 at 9:53 and it wasn't letting me. Should I just email you?
That would happen.
Okay.
Okay.
Thank you.
You're right. I think, yeah, I'm not sure why. So it means everybody lost the last answer. But everybody had to send me an email anyway with the picture. Yes.
Hi, so I have a question. So there was like this day, I think it was the first week of June, the Friday, and then like in the morning I wasn't feeling well. I emailed you like at 7 for like an hour before. I emailed you too for like what I'm saying now. And then so I saw in the syllabus that say that you're allowed to miss like up to 5 lectures. So I was just wondering like how like because I